Hello everyone. In this session, we'll discuss about A to D converter or analog to digital converter. So basically, we use these kind of peripherals in modems where it is required to convert the digital signals into analog form and analog signals into digital form. As well as we do use these kind of peripherals while interfacing some kind of sensors to the controllers or to any kind of real devices. We require these kind of converters because these converters will give us the digital information by sensing the data of the real time. Okay, so let us see about this A to D ADC converter inside a PIC controller. So initially we'll see the internal structure of this A to D structure. So as you can see, it is an 8-channel ADC. Now it can receive the inputs from 8 analog inputs or 8 analog channels. As you can see here, RE1, RE0 and RE2, that is port E and port A. By default they will be acting as analog inputs. Now out of these 8 analog inputs, only one of the analog input will be selected and that particular input will be processed by this A to D converter. Okay, now that selection is done by some selection lines. As you can see here, CHS2, CHS0. So these selection lines are used for selecting one particular input channel. Now that is given to the converter, so converter will process that input and will give us the 10-bit digital data. Okay, now here the V reference, that is reference voltage, positive as well as negative, can be connected in two ways or can be given in two ways. Okay, one is by using the supply voltage, that is VDD and VSS, directly connecting these pins to positive as well as to negative. Okay, and the other way is we can also give this reference voltage positive and negative from the external pins. Okay, so as you can see, those external pins are RA3 and RA2. Okay, so if you want to give these reference voltages from the external pins, then we have to configure some pins, okay, or some registers. Okay, so if you configure these registers, then this converter will be getting the reference voltage from the external source. Okay, if you don't want that, if you want only the supply voltage as the reference voltage, then directly connect these positive and negative terminals of this reference voltages to the supply, that is positive and negative, VDD and VSS. Okay, so this is how the converter is going to process the input out of 8 inputs and gives us 10-bit data. Okay, let us see the registers which we need to program in order to use this A to D converter in this PIC controller. So we have to access ADCON 0, ADCON 1, and then we have result register like ADRESH and ADRESL. Now it is a 16-bit register. Okay, and it has been divided into two 8-bit registers, that is ADRESH. H indicates that is MSB bits and L indicates the lower byte or else the LSB bits. Okay, so the last result, that is 10-bit digital data, will be stored inside this particular result register. Okay, now let us see some of the important points of this A to D converter. As you can see here, the converter generates a 10-bit digital value corresponding to the analog input. So corresponding to the analog input, it will generate a 10-bit digital value. Okay, and the reference voltages, as I told you, that reference voltages can be given in two ways. One is by using that is a VDD and VSS, or else you can also give these reference voltages through the external pins RA2 and then RA3. Okay, and then we have ADCON 0, which is going to control the operation of A to D converter. As every time I say that whenever we come across a peripheral, we do come across one registers which controls the functionality of the peripheral, that is control register. So here CON 0, that is ADCON 0, will control the operation of the A to D converter. And then ADCON 1, now this control register is used for setting the port A as well as port E pins to act as analog inputs. Okay, so if you want to use these pins as analog inputs or else as reference inputs, then we have to use this ADCON 1 register. Okay, anyhow by default port A and port E will be acting as analog inputs. Okay, next, the converted digital output is written into the result register, that is ADRESH and ADRESL. Okay, let us see each and every register and the importance of each and every bits. Now as you can see, ADCON 0, it's an 8-bit register. So we'll start discussion of this from its MSB. Now ADC S1 and ADC S0. These are the two bits by which we can select the clock source for the peripheral, that is ADC peripheral. Okay. Now this clock source can be given in two ways. One is directly giving the processor clock by dividing it with some factor, or else we can also directly give it by using the RC oscillator, which is internally present inside the ADC converter. Okay. Now if you are programming these two bits with 0 0, then it means the processor clock gets divided by 2 and then it is given as a clock signal to the ADC converter. Okay. So in the same way you have 4 combinations, as you have 2 bits, so we'll get 4 combinations. So each and every combination will have its own importance, like a F oscillator divided by 8, which divides the processor clock by 8, and then the last combination 1 1, where you'll get the clock directly from the RC oscillator. Okay. And then you have bits like CHS 2, 1 and 0. Now these bits are used for selecting the channel. Okay. So we can give, at a time we can give 8 analog inputs, but the thing is converter can process, that is ADC can process only one particular input. Now that input is selected with the help of these bits. Okay. So if you are programming it to 0 0 0, it means you are processing, it means ADC is now processing channel 0. Okay. So channel 0 is nothing but RA0. So whatever the input that you are giving through analog input 0 or RA0, now that will be processed and you'll be getting the 10-bit digital value. Okay. And so as you have 3 bits here, so you'll get 8 combinations, so 8 analog inputs. Okay. And then you have go or done bit. Now when you want to start the conversion, just program it to 1 so that the conversion starts. Okay. And after conversion, now this bit will become 0, indicating that the conversion has been completed. So after making it to 1, we have to poll, if you are not using interrupts, then we have to poll this particular bit, or we have to monitor this particular bit until it becomes 0. So as it becomes 0, it says that conversion has been completed. Okay. If we are using interrupts, then we can perform some other operation. We can program this particular bit to 1, and then we can perform some other operation. And when an interrupt is generated, then the processor will execute the ISR, where we have to write the result, or where we have to write the respective code for reading the result register. Okay. So we have to program it to 1 for starting the conversion, and we have to monitor this particular bit until the conversion takes place. Okay. So after conversion, this bit will become 0. Okay. And then you have ADCON. Now this bit is used for turning on the peripheral or turning off the peripheral. So if you want to turn off the peripheral, make it to 0. If you want to turn on the peripheral, then make it to 1. Okay. So this is how we are going to use this ADCON 0 register. Okay. So by using this, we can select the clock source, and we can also select a particular channel, and then we can start the conversion, and we have to monitor this conversion bit. Okay. And as it becomes 0, it says that conversion has been completed, and then we can also turn on as well as turn off the converter by using this particular bit. Okay. Now let us see one more register, that is ADCON 1. Now ADCON 1 will start from this LSB bits, PCFG, which are nothing but port configuration bits. Okay. Now by default, all these are zeros. So all these are zeros in the sense all the channels or all the port A and port E pins are now acting as analog inputs. As you can see here, A indicates analog inputs and B indicates digital input output. Okay. So here they'll be acting as analog inputs. Okay. And by default, V reference would be VDD and V reference minus would be, that is, ground VSS. Okay. So if you want something like V reference should be given from the external source, that is V reference positive should be given from the external source, then you have to program these 4 bits with this combination, that is 0001, so that all the pins will be acting as analog inputs except RA3, by which you have to give the V reference positive, and V reference negative of the peripheral is connected directly to VSS. Okay. So according to our requirement, we have to program these particular 4 bits. Okay. So as we have discussed about these 4 bits when we have seen the GPIOs of a PIC controller, so I've told you that whenever we want to use port A and port E, then we have to configure these particular bits to either as 0, either to 6 value or else to 7 value. If you can see here, 011X. Now X can be 0 or else it can be 1. If it is 0, then it becomes 6. If it is 1, then it becomes 7. Okay. So if you program this particular combination into these bits, then what's happening here? So all the channel pins are now acting as GPIOs. Okay. So that's the reason we have programmed these 4 bits to either to 6 or else to 7. So according to our requirement, we can select any one of the combinations. Okay. So if you want V reference plus and V reference minus to be given from the external source, then you have some combinations like 1000. As you can see, all the inputs are now acting as analog inputs except RA3 and then RA2. Okay. So and then we have the 3 unused bits which are not used in 16F877a series, and then we have the last MSB bit which is ADFM, A to D result format select bit. Okay, so we know that after conversion the 10-bit result will be stored inside the result register, but where we have to store? So if I want to store the result in write justified format, then I have to program this particular bit to logic 1. Okay, if I want to store it in left justified format, then I have to store it in, that is I have to program this particular bit to 0. Okay, let us see what is that right and left justified. Now as you can see this, if ADFM is programmed to 1, then it is write justified. So whenever the result is write justified, then the MSB bits are programmed with or are appended with zeros. Okay, and the result will be stored inside the LSB. Okay, and if you are programming it to 0, that is ADFM is programmed to 0, then it means left justified, where you can see the LSB bits are now appended appended with zeros, and the result is now stored from the MSB of the result register. Okay, so this is how we can store the result into any one of the format. And then we have here PIR1 and PIE1. As every time I say that for every interrupt we have 2 flags. One is interrupt flag and the other one is interrupt enable flag. So whenever we enable the interrupt, then if an interrupt is generated, then the processor will execute the ISR. Okay, so if you want to use interrupts, then we have to program this particular bit to logic 1 so that the interrupt is enabled. Okay, and whenever an interrupt is generated, so when actually the interrupt is generated, when the conversion is completed. Okay, so when the conversion is completed, then this particular flag will become 1, indicating that conversion is completed. And if you have enabled this bit, then the processor immediately executes the ISR, and then after execution of ISR, it will resume the main task. Okay. Now let us see the procedure which we need to follow for converting a particular signal to digital form. Okay, so the first step that we have to follow is configure analog inputs. So we have to configure the analog inputs according to our requirement by using ADCON 1 register. Okay, whether we want to use all the inputs as analog inputs, whether we want to use some of the inputs as analog inputs and some as digital inputs, or whether we want to use some as analog digital and then reference inputs, so that can be done or programmed with the help of ADCON 1 register. And then here we have to use ADCON 0 for selecting a particular channel. Okay, and then so we again have to use ADCON 0. So here we need to select the clock source. Okay, a particular clock source like the processor clock divided by 2, or else processor clock divided by 8, or else giving the input from the internal RC oscillator. Okay, and then we have to turn on the module. And if we are using interrupt, so if we are using interrupt, then what we have to do is we have to clear this ADIF bit so that interrupt will not be generated immediately. And then we have to set GIE and TEIE. Okay, GIE is global interrupt enable, that should be enabled always for generating an interrupt, and TEIE is a peripheral interrupt enable. Now as we are generating the interrupt with the help of peripheral, then definitely this particular bit should be enabled. Okay, and then ADIE bits. Okay, so ADIE is present inside this PIE register. Okay, so we have to set all these 3 bits so that if an interrupt is generated, then the processor will execute the ISR, and then we have to wait for a required amount of time so that the capacitor will be charged. Okay, sample and hold circuit will be used inside this. Now the capacitor gets charged, and then we have to start the conversion. So conversion is started by programming logic 1 to this go or done bit of ADCON 0. Okay, and then we have to monitor this go or done bit until it becomes 0 if we are using polling method, or else we have to carry on some other operation in our main task. Okay, if an interrupt is generated, that means whenever the conversion is completed, then the processor will be executing the ISR, where we have to write a code in such a way that it has to read the result from the result register. Okay, and then read the A to D result register pair, and then we have to clear the ADIF if we are using interrupts, and then we have to repeat the same process. So this is how we are going to use ADC converter for converting the analog input into digital form, and we can also read the data in 10-bit digital form, that is from the result register.